Okay, so let's go throughout the quadratic form example that ChatGPT gave me just in order to show you how can I find the rank of a quadratic form and how can I find the signature of a quadratic form. So quadratic form is built from a symmetric matrix that represents it, and let's start by showing you this is a quadratic form. It has coefficients and variables, and this is a quadratic form with three variables. So I can represent this quadratic form in this order where A is a square symmetric matrix, and it's very important that it's a symmetric matrix, don't forget this. So I can present this quadratic form in a matrix, the coefficients in a matrix. Now the coefficient between the, let's call it the variables that are only from one variable is on the diagonal, and when there are two variables or more depending on your quadratic form, they are not in the diagonal. So for example, for this quadratic form, on the diagonal we have 3, 2, and minus 1. So you can see it right over here, 3, 2, minus 1. And for x, y, sometimes they tell you x1, x2, you have 4, so you split it, so it's 2 here and 2 here. Think about x as the first row and y as the second column, or the second row you want. So 2 plus 2 should be xy, so it's 4, so this is here for xz. Z, let's call it a third, so x first, so here is the xz, and again I divided by 2, so minus 2 divided by 2 is minus 1, so here is minus 1, here is minus 1. You see the symmetric, so you can see here where the coefficient came in each position. Anyway, it's like I just did. So we continue after we represented this quadratic form by the symmetric matrix that represent this quadratic form. We can go to find the rank and the signature. We'll do it throughout the eigenvalues of this symmetric matrix. Now remember that symmetric matrix in the symmetric matrix is always diagonalizable because it's a type of a normal matrix. So its algebraic multiplication of each eigenvalue will be equal to its geometric multiplication. Keep that in mind. So in order to find the rank and the signature of the matrix that represent the quadratic form, or I should say, if I want to find the rank and the signature of the quadratic form, I will find the eigenvalues of the representing matrix of this quadratic form. How will I do that? Like I do for every matrix for finding the eigenvalues. I will do a determinant of A minus lambda I the equals 0, so I will just solve this. You can see the solution. Anyway, I'm not even sure that he was right in his calculation, but it really doesn't matter. The only matter is that he came with eigenvalues values. So if we are finding the eigenvalues, here they are. Maybe there are mistakes in calculation, I don't know, but it doesn't matter. We get to the eigenvalues. You can see here that I have three eigenvalues totally, so the rank would be 3. I don't have repeated. Even if I had repeated eigenvalues, each repeat eigenvalue I count as 1. If I have 3 times the same eigenvalue, it's 3. Okay, so I have here 3 eigenvalues, so the rank of the matrix is 3. So the rank of the quadratic form is also 3. So here we found the rank of the matrix. Now the signature of the matrix is take the number of positive eigenvalues, take the number of negative eigenvalues, and you can see here the signature. Sometimes to evaluate the signature, we do the number of positive eigenvalues minus the number of negative eigenvalues. So it will be just 1. Or you can do it like this, depends on your institution, things like this. So you can see here the summary of this exercise. You can see the quadratic form, the represent this symmetric matrix, the represent this quadratic form, the eigenvalues, the rank, the number of eigenvalues, and the signature, the number of positive eigenvalues and negative eigenvalues. Okay? So I think that this is it for now. This was an exercise on the quadratic form and how to find its rank and signature. Thank you very much. Thank you for the GPT. Even if it was wrong in the calculations, I don't care because the idea was what I wanted to show. And that's it. Thank you all very much as well.